All right, let's talk about something we all use literally every single day. But how many of us actually know how it works? I'm talking about the refrigerator. You know, that box of everyday magic. Today, we are going to open that door and pull back the curtain on its secrets.
So let's just start with the biggest question right off the bat. How on earth does this machine make things cold? I mean, it seems to defy the laws of nature, right? Everything wants to reach room temperature, but this box just doesn't. It feels like it's breaking a fundamental rule of the universe, doesn't it? Well, here's the secret. It's not.
And this right here is the single most important thing you need to get. A fridge doesn't create cold. It's not a cold factory. It's a heat mover, a heat pump, really. The best way to think about it is like a bouncer at a club, grabbing all the unwanted heat from inside and literally throwing it out into your kitchen. That's it. That's the entire trick.
Okay, so let's get into the nitty-gritty of how this actually happens. The hero of our story, the thing doing all the heavy lifting, is a special substance called a refrigerant. And you can think of it as our dedicated little heat-moving employee, going on a continuous, four-step journey to keep your leftovers fresh. So, step 1. The journey starts inside the fridge, in these coils called the evaporator. Right now, our refrigerant is a super cold, low-pressure liquid. As the warmer air from, your food circulates over these coils, the liquid refrigerant basically acts like a sponge. It just soaks up all that heat. And in doing so, it actually boils and turns into a gas.
All right, step 2. That gas, which is now carrying all the heat it stole from your food, travels to the heart of the whole system, the compressor. Yeah, that's the part you hear humming in the kitchen. And the compressor does exactly what it sounds like. It squeezes that gas hard. This squeeze massively increases its pressure, and because of physics, its temperature skyrockets. So now we have a very hot, high-pressure gas. Step 3. This super hot gas flows into another set of coils, the condenser coils. These are the ones usually on the back of your fridge that feel warm if you touch them. And because this gas is way hotter than the air in your kitchen, all that heat it was carrying just radiates out into the room. As it dumps the heat, the refrigerant cools down and, you guessed it, it condenses back into a liquid. Still under high pressure, though.
And now for the grand finale, the big reset. Step 4. That high-pressure liquid gets forced through this tiny, tiny nozzle called an expansion valve. And when it comes out the other side, whoosh, the sudden release causes its pressure and temperature to just plummet. And just like that, we're right back where we started. A very cold, low-pressure liquid, ready to go back into the evaporator and grab more heat. And that cycle just goes on and on and on.
So there you have it. That's the four-step dance our little refrigerant does, over and over. But, not all refrigerators are created equal. Some are just better at this dance than others. So how do we actually score their performance? How can we measure how good they are at their job of moving heat?
Well, in the world of engineering, there's a specific term for this. It's called the coefficient of performance, or just COP for short. And it's actually a pretty simple ratio. You just take the amount of cooling the fridge provides, the heat it removes, and you divide that by the energy the compressor had to use to get the job done.
Yeah. In other words, it's basically asking, how much cooling bang do you get for your electricity buck? And that's really the heart of it. The COP is the ultimate efficiency score. The higher the number, the better the refrigerator, and of course, the lower your energy bill.
So what's a good score? What are we looking at here? Well, for a typical household fridge, a COP of around 3.5 is pretty common. And think about what that means. For every single unit of electrical energy the compressor uses, it's able to move 3.5 units of heat energy. That's actually really impressive when you think about it.
But here's where it gets interesting. That COP score isn't fixed. Engineers have figured out all these clever ways to tune the cycle, to tweak it. And these small changes can lead to a much bigger cooling bang for your buck. It's all about making the system work smarter, not harder.
So that kind of begs the question, right? What actually changes the COP score? What are the things that make it go up or down? Well, it turns out there are a couple of really big factors at play here.
First up, and this one is huge, is the temperature you set your fridge to. I mean, it matters a lot. Look at these numbers. If the system is straining to keep things at a super cold -20 Celsius, the COP is only 2.63. But if you set it to a more moderate 10 degrees, that score more than doubles to 5.35. The takeaway is simple. The less work the fridge has to do, the smaller the temperature difference it has to maintain, the more efficient it's going to be.
Okay, the second big factor is the temperature outside the fridge, in your kitchen. Think about it.
In a really hot room, say 50 degrees Celsius, it's much harder for the condenser to dump its heat, right? And the COP plummets to 2.63. But in a cooler, 30-degree room, it's way easier, and the score jumps to 4.58. This is exactly why you should never, ever put your fridge in a hot, stuffy garage or a tiny, unventilated closet. But wait, there's more. Beyond just playing with temperatures, engineers have another pretty cool trick up their sleeves to squeeze out even more efficiency. It's a clever little optimization, a real pro tip called subcooling.
So what in the world is subcooling? It's pretty simple, actually. It's just the process of giving that liquid refrigerant an extra little chill after it leaves the condenser, but before it goes through the expansion valve. By doing this, you make sure it's as cold as it can possibly be right before it starts its heat-absorbing job again. It's like giving your sponge an extra squeeze before you use it, so it can soak up even more water. And you can see the difference it makes right here. A standard cycle might get a COP of, say, 4.56, but just by adding that subcooling step, the same system can hit 4.74. Now, I know that might not sound like a huge jump, but think about it. Over the 15 or 20-year life of a refrigerator, these tiny little efficiency gains add up to some seriously massive energy savings.
Okay, so we've been deep in the weeds here, talking about COP scores and subcooling. But let's zoom out. Why does all this stuff matter? Why should we care about squeezing every last drop of performance out of this cycle in the real world?
Well, the impact is, frankly, it's enormous. On a personal level, a higher COP, that means real money saved on your electricity bill. For society, it means less overall energy consumption, which puts less strain on the entire power grid. But it's even bigger than that. This constant push for efficiency is what makes our modern global food supply chain possible. It's what makes life bearable, even comfortable, in the hottest climates on Earth. This isn't just about a kitchen appliance. We're talking about a true cornerstone of modern civilization.
When you really stop and think about it, that simple cycle humming away inside your refrigerator is one of the most important technologies we have. And as our world gets hotter, the race isn't just about making things cooler anymore. It's about doing it smarter, more efficiently than ever before. Which really leaves us with a final, big question to chew on. In this hidden but absolutely essential technology, what will the next big innovation be?